introduction. As explained, so today's talk will be about AI for healthcare, prediction and interpretation, multimodality. So 3 parts. So with a brief introduction, I'll move on to the main material, and hopefully I can cover all 3 within the given 15 minutes. All right. So a little background of me. I graduated Georgia Tech back in 2018 in summer, and my main thesis was actually right here, interpretable deep learning for electronic health records. So I mainly developed new methods using neural networks to handle electronic records and make various predictions while making it as interpretable as possible, which I'll talk about today. And before joining KAIST last 2020 spring, I used to work as a developer in Google Brain Health for about 1.5 years, extending my research from PhD time. Right, so dive right into the main material. So predictions. So before we actually move on to interpretability and multimodality, which is a bit more advanced topic, I should probably lay down the groundwork first and try to convey how to describe how to use neural networks as easily as possible to build a most basic prediction model based on electronic health records. So that's what I'll be talking about. This work is based on what I did in Sutter Health back in 2015 summer, which I was a research intern back then. And the project they gave to me was to actually predict heart failure. So given about 30,000 patient record, they wanted me to come up with any methodology that I wanted. So it was totally on my own liberty to come up with any methodology to predict heart failure as accurately as possible, because heart failure in America especially is a very widely spread disease. It's a very critical disease as well. So as written here, 1 in 5 adults are suffering from heart failure, and those who are admitted to the hospital, about 50% of them would actually expire within 5 years after the discharge. So it's a very high cost and high mortality disease, and it's a very severe issue in the United States. So that's why they wanted me to predict heart failure as early as possible. So this is a healthy heart here and a failing heart over there on the right side. And it's rather easy to diagnose a failing heart at the last minute, because there are a lot of explicit symptoms that can easily indicate heart failure, which is like dysrhythmia, cardiomyopathy, atherosclerosis, heart failure disorder. These are a clear indication that your heart is failing. But diagnosing that you already have a heart failure doesn't really help the patient, because there's not a lot you can do. So you have to pre-diagnose, or you have to actually predict that certain patient will get heart failure at least like 6 months earlier, or maybe a year earlier, prior to the diagnosis, prior to the index stage, so that you can actually do something, try to recommend a certain diet, or maybe apply ACE inhibitor, that kind of stuff. But it's hard because a year or maybe 6 months prior to the index date, the signs are pretty subtle, like hypertension, shortness of breath, or diabetes. These could easily be just adult disease that people just usually get after when you get old. So doesn't really indicate that if you have hypertension, then you're going to have heart failure. That's not the case. So that's why we turn to neural networks to pick up the subtle signals that only the machines can recognize when a lot of data is given to the model. So that was the motivation, and this is the diagram that I usually prefer to depict the patient record over time. So it's based on outpatient records. So the patient comes to the hospital maybe 3 times in his or her lifetime, and at each outpatient encounter, multiple things happen. You get a bunch of diagnoses, and you get prescriptions, and you get procedures, and that kind of stuff. Maybe some labs as well. So each visit can be seen as a set of medical events or codes, if you will. And given all the visits the patient made so far, the task is to actually predict whether the patient will have heart failure within 6 months, or maybe a year, or maybe 3 months. That's actually a hyperparameter that you can predefine. So given this, the classical, before the deep era, before the rise of deep learning, the classical method was to actually how to modify, or how to process all the information given to us as the form of electronic health records, how to process that into a vector, so that we can feed that into the machines, and then try to use random forests, or support vector machines, or logistic regression to make a prediction. So that part was mainly done based on relying on domain knowledge. So there would be like a cardiovascular expert who knows a lot about heart failure, would tell the IT engineer to build a predictive model based on his or her intuition or his or her expertise on the matter. So for example, like in order to predict heart failure, you need to count the number of times the patient has gone through arrhythmia, or the number of times the patient, or whether the patient has ever been prescribed with diuretics, that kind of stuff, like all like very specific domain knowledge. And based on that, you would create so-called patient representation vector. So this vector is the summarization, is a summary of everything that happened here. And this is clearly it's a pretty interpretable representation. On the first dimension, you count the number of times arrhythmia happened. The second dimension, you count the number of times respiratory failure has happened, something like that. But in deep learning or neural networks, not only patients can be viewed as or represented as a vector, everything can be represented as a vector. So even a single diagnosis, single medication code, a single procedure code, they can all be represented as a certain dimensional vector, like n-dimensional vector. And the number n can be up to us. It could be 128, it could be 256, it's up to you. And the values within each vector, as opposed to here, we clearly know what the values in each dimension represents. But here, we actually don't know. We don't know what the ideal value for cough would be in each dimension. So that is all learned by machine learning, by deep learning, actually, using backpropagation. So if properly learned, then these diagnosis vectors here, like, or medication vectors here, or procedure vectors here, if properly learned, they would be very well organized in that n-dimensional space. This happens to be two-dimensional space for visualization, but in n-dimensional space, they would be very well organized. You know, like similar diagnosis or relevant diagnosis code would be located in the same region, and irrelevant ones will be farther away. So this is one of the visualization of that example. So given that knowledge, where everything can be represented as vector, then you simply, given this record, you turn everything into a vector. So cough, fever, pello, obviously these codes can all be represented as a vector, and since they all happen within the same encounter, you can actually sum them up to make them into a visit representation now. So that these three visits are now all turned into a vector, and then you can actually sum these vectors up to obtain the final patient representation, because a patient is, after all, just a sequence of visits in my diagram. So you can actually add them up again, but then simply adding these three vectors would actually destroy the order between visits, because visits have a sequence within each other. So visit 1 came before visit 2, and so on and so forth. So in order to retain that information, we use something called recurrent neural networks, RNN. So we have 3 visit vectors. We feed them in one at a time into the neural network. And then the final hidden layer here would be now our final patient representation vector. So given this, we can plug that into SVM or whichever you want, logistic regression. And then you would train the learnable parameters, the coefficients of all of this model from end to end in an end-to-end manner. So if the logistic regression score is 1, then it means that this patient will have heart failure. If it's 0, then this patient will not have heart failure. So that would be our basic setup. And we can actually, I've actually experimented, conducted an experiment with this model using these 33,000 patient records, and where I used all the medical codes that I could get my hands on. And the performance was actually pretty distinguishing between the classical models and the RNN-based neural network-based models. You can see that the AURC is above 85, whereas logistic regression is below 80. So it's clearly there's some potential with deep learning. But the problem is that there's some interpretability issue that, as Dr. Guan actually discussed before my session. So in order to tackle that, what I did is, the question is, if the model makes certain prediction, then why did the model make such prediction? Like if the model says 90% risk of heart failure risk in the future, then there must be a reason for that. And the reason is actually broken down into 2 aspects, where the first aspect is which visit or which encounter contributed to the final prediction, and within each encounter, which code or which medical event contributed more to the final prediction score. So based on these 2 questions, which the visit importance and the code importance, we can think of a model that can actually answer these questions by using something called attention mechanism. So attention mechanism is neural network technique where the neural network model will decide which feature or which information is more important, which is not, based on maximizing the accuracy or the performance of the model. So based on that, we can actually draw explainable model, visualize this prediction. For example, here, this patient has made about 10 visits overall, where the x-axis is a time axis, and each visit, a couple of codes were given to the patient, and the final risk score was 24%, 0.2474. And you can see that the heart-related codes receive higher contribution or make higher contributions, and more recent codes get higher contributions. Like the same CV, same cardiac dysrhythmia, even though they're the same codes, the more recent information is giving more contribution towards the final prediction. So you can see that it is working actually pretty accurately. The final slide topic is multimodality, and since I don't have a lot of time, I'll have to actually gloss over the main material. So the motivation is that the EHR consists of multiple modalities, not just codes that we just talked about, but also free text notes, spectrograms based from the EKG, pixels from MRI, CT scans, X-rays, continuous values from vital signs, and just your weights, your labs as well, lab values as well. Lab results will also be continuous. So all these heterogeneous multimodal data or information make up the patient representation. So based on that, we did some experiment trying to mix the two, the X-ray images, which are the pixel information, and the X-ray radiology report, which is the textual information, and try to mix the two together into a same model. And we could notice that the model was actually recognizing certain medical terms into the pixel region. So it is here you can see that this pulmonary edema, which is a medical term that the model has no knowledge about, but after looking at thousands and tens of thousands, hundreds of thousands of images and radiology report, the model is now able to recognize pulmonary edema is actually right here, and pleural effusion is right here. So it's able to link the information between textual world and the pixel world simply by looking at hundreds and thousands of images, which is pretty impressive. Because I for one didn't inject any domain knowledge before training, so it was all data driven. And you can see that it can also even write reports for radiology report based on X-ray images. So here, this is the original report, and this is the generated report, and you can see that as opposed to original report using abbreviated terminologies like ET tube or NG tube, model prefers to use endotracheal tube and nasogastric unabbreviated terms, which is a bit more, which was quite an interesting phenomenon. It's something that we can further study in the future. So multimodalities is just one example, because I was just showing how to mix the pixel information, textual information, but you can also mix the structured information like codes and unstructured information like discharge summary, and try to mix the two together and see how the model understands multimodal medical data. And it's just the beginning. And if we can actually mix 3 or 4 different modalities, but then mixing multiple modalities will lead to engineering problems. So that's another venue that we can explore in the future. Thank you very much for listening to my talk. Thank you very much. Bye-bye.